Great. Well, it looks like we've got lots of folks logged in here. I will go ahead and kind of get us started. Welcome, everybody. My name is Maya Swope, and I am the Outreach and Volunteer Coordinator here at Friends of the Boundary Waters Wilderness. Very excited to see all of you on here today and to have a great presentation on geology and the boundary waters. Kind of a few notes of things before we get started. We do have an option for closed captions. So for the subtitles today, you can either turn that on or off by clicking the CC button that's kind of at the bottom of your screen, or you might have to click more to see that depending on what your settings are. We also do have the chat function. So if you have any comments throughout or sort of technical questions or things that you want to bring up, the chat button is a great place for that. And then any more questions that you have for the presenter, we will try to get to at the end today. And there's a separate Q&A function at the bottom of your screen as well. So any questions that come up throughout the presentation, feel free to put those in there and we'll get to as many as we have time for towards the end. For anyone who is not familiar with Friends of the Boundary Waters, we are a nonprofit that's been working to protect the boundary waters and surrounding ecosystems for more than 40 years. We do a lot of different programs, from wilderness education, from advocacy, from legal battles to fighting mining. We're really kind of trying to work at the intersection of people, of wilderness and community, and bring it all together in our work as a nonprofit. And you can find out more about us. I will send out links to our website and some of our other resources to everyone that registered here today. So I think with that, let's get into the presentation. I'm really excited to have Rudy Molinek here. He is a PhD student at the University of Wisconsin-Madison. He has a lot of experience podcasting and writing and studying about geology and the landscape. And Rudy, I will go ahead and turn it over to you.
Awesome. Thanks so much. And thanks everyone for being here. So today I am going to talk about the long geologic story of the boundary waters, and it is really long. So I want you to keep in mind as I'm going through here that I'm talking about a bunch of different events that happened over the course of the deep past, and any one of these events someone could spend their whole career studying and still not understand fully. So I'm trying to keep it at that bird's eye view. So there's tons more depth than I'm going to be able to get into today. So what that really means is there's lots for you to explore if you find something you're interested in. I also want to say, so this picture here is taken by a friend of mine, Ethan Parrish. And so he has some great photos of the boundary waters that he shared with me that I'll sprinkle in today. So the really beautiful landscape photography that you'll see is not my own, it's Ethan's. I guess all other images I should say I either attribute them to their source or they're from sort of an open access source. So a little bit about me, as Maya said, I'm a PhD student at University of Wisconsin-Madison, but I grew up in North Carolina and I first moved to Minnesota to go to Carleton College in 2011. And right from the start, I fell in love with the landscape of the Midwest. I joined the local, or the college's outdoors club. And so the first weekend actually of college, I went up to the Superior Hiking Trail and was just blown away. I had no idea landscapes like that existed in the upper Midwest. And then that first winter, I did my first ever winter camping trip at Gooseberry Falls State Park up on the North Shore. And then a few weeks later, went snowshoeing in the boundary waters. So I always thought that I wanted to move to the mountains. And I did live in Montana for a couple of years after I did my master's at University of Minnesota. But here I am back in the Midwest. And a big part of that is just being in love with the landscape of the Northwoods and the boundary waters area and northern Wisconsin, just anywhere around Lake Superior. I absolutely love it. I make a podcast that the first season is fully out now, and it's about the geology of specifically Wisconsin, but a lot of the stories are the same and apply to Minnesota too. So check that out. At the end of this talk, I'll point out some of the particular episodes which specifically apply to the boundary waters. So I wanted to start off with an introduction to geologic time because we're going to be working through a lot of time here. And so the way that this is arranged, the oldest time, sorry, my mouse is being funny. Okay, anyways, so the laser pointer's not working on my end, but I'll try to just go through here. So the bottom right is the beginning of Earth history. So down at the bottom of that Precambrian column, and then it gets younger as you go up, and then it jumps over to the left. So this column over here, the Paleozoic, the bottom of that lines up at the top of the Precambrian, and it goes through from there. But this is a really misleading way to look at time, because that first column on the right, the Precambrian, is 4 billion years. That's 4,000 million years. So it's a huge amount of time in that right column, whereas the left column, the most recent, is about 65 million years. So it's a little bit skewed. But even looking in the skewed, I'm going to show you some like milestones of Earth history to sort of orient us to time. So the first life forms came about 3.8 billion years ago. So that's 3,800 million years ago, are the oldest bacterial life forms. The Cambrian explosion is 540 million years ago, and that's the first large-scale occurrence of skeletal life. So creatures with skeletons that were swimming around in the oceans. And that's 540 million years ago. I spent a lot of time in southern Minnesota looking at the limestones and sandstones down there. Those formed about 400 million years ago. The extinction of the dinosaurs, that big asteroid, happened 65 million years ago. North America started being covered in glaciers about 2.5 million years ago. And the first humans are really like basically now. So we're really, really recent. But I wanted to take this kind of skewed look at geologic time and put it to scale. So here, the oldest stuff, the beginning of the Earth, is on the left, and it gets younger as you go to the right. And so I'm going to put those same events up. And this is to scale, so it doesn't blow up the more recent past. So here's the oldest life, 3.8 billion years ago. Here's the Cambrian explosion, where those first skeletal life forms came at about 540 million years ago. The southern Minnesota sediments at about 400 million years ago. The extinction of the dinosaurs at 66 million. The beginning of North American glaciations at 2.5. And then people there. So you can see that really a lot of the milestone events are really tightly clustered in the more recent past. And we actually don't know all that much about what happened in the deep past. So now what I want to do is take this time scale and put it onto the boundary waters. So what geologic events happened and when in the boundary waters. So for each of these that I'm about to show, I'm going to go into them in more detail later on, and also talk about some common rocks that you might actually see if you're up in the boundary waters. But for now, I'm just going to put them on this time scale. So the oldest rocks in the boundary waters are here at about 2.8 billion years ago. That's 2,800 million years ago. And that's the Canadian Shield and Superior Craton. So we'll get into what all those words mean in a minute. I just want to sort of orient us in time, but those are the oldest rocks in the boundary waters. Then at about 1.8 billion years ago, we had the Pinocchion orogeny. And again, orogeny, I'll explain what that means later, but this is the geologic event where we get the iron formations, which are a really important part of the story of the arrowhead up there. Then at about 1.1 billion years ago, we have this event called the Mid-Continent Rift, which is involved in the copper deposition. So another really important part of the geologic history for the region, and one that's really relevant right now, as we'll talk about at the end, as I'm sure you as fans of the boundary waters are all familiar with the copper mining that's being proposed currently nearby. And then the glaciations, which they started in North America about 2.5 million years ago, but they probably got to Minnesota at about 2 million years ago. So just to summarize geologic time in the boundary waters, it spans 2.8 billion years of Earth history up there, which is really, really incredible. And it's so incredible, it's more time than you would see if you took a rafting trip down the Grand Canyon. So the oldest rocks that you would see in the Grand Canyon are only 1.7 billion years ago old. So the rocks in the boundary waters were 1 billion years old by the time the rocks in the Grand Canyon first formed. All right, and so we've looked at these events through time, and now I want to break it down a little bit in space. So how are these rocks arranged spatially? So I put this on this slide for two reasons. First, if you're here and you're interested in geology and you're in Minnesota, or really any other state, they have these books for pretty much every state now, I think. And it's an incredible resource for someone who's interested in geology. So I just wanted to give a shout out to this book. If you're someone who's interested, it's a great thing to have on your shelf. But what the image that we're seeing here on the front is what we call a geologic map. So these colors correspond to different rock units, different types of rocks, and they represent what you would see if you were to strip away all the soil and debris and everything until you got to solid bedrock. So that's what we're looking at here. Every different color is a different type of bedrock that's beneath all the soil. And just by looking at it, you can see that there are different geologic provinces of Minnesota. So in the bottom right in southern Minnesota, you see those kind of light blues and yellows are the big sedimentary sequences that is down in that part of the state. And things get a little bit more complex when you get further north. And each one of those black lines is a fault or a fracture where the rock has moved at some point. So we'll get into that. But I wanted to zoom in here to the boundary waters area and talk about those events that I mentioned on the time scale and sort of see how they play out in space. So the first is that Canadian Shield. Those are the really, really old rocks that are about 2.8 to 2.7 billion years old. And so they occur, they're these like pink and blue and green rocks on this geologic map. And you can see that there are a lot of faults in there, all those black lines, and those will be important later on. The next little area in the bottom left is the Pinocchion orogeny. And so that little thin red line at the top of it, not the one I drew on, but the one that's part of the map. And see if my laser pointer is still being funny. And oh, there we go. So this line there is the Mesabi range. So that's the iron formations that were historically mined. And there's another little bit of the Pinocchies up here, and that's the Gunflint iron formation up in that little corner up by Gunflint Lake. And then the remainder of this is mid-continent rift rocks. So we'll talk about what all these mean. I just want to sort of orient you in space before we get started. And then of course the glaciers came and went over all of this. So this map doesn't show anything about the glaciers, but they changed the landscape across all of Minnesota, really. Okay, so back to the time scale, and we're going to start with those oldest rocks in the Superior Craton of the Canadian Shield. And so this is a map of all of North America, and each of these different areas is a different little piece of rock that were all assembled around this time to make up the core of North America. So if you go back before 2.8 billion years ago, the Earth would not have looked like today with a few big supercontinents, like we have 7, but all over the Earth. It would have had lots of little pieces of land sticking out all over. And around this time, they were being assembled or stitched together. So the pink colors on here are those little bits of land that would have been sticking out. And then the stippled areas with the polka dots are the areas where they got smushed together. And so we're going to see both of those. And let's zoom in here. This is a map from a Quebecois geology organization. And so the names are in French, but that I guess you might be used to that in the Boundary Waters if you go into the Quetico too. So the Province de Lac Supérieur is the Lake Superior craton of the Canadian Shield. And so that's one of these, it's a volcanic area that would have been sticking up above water 2.8 billion years ago. And then the Pinocchion orogeny is that stippled area. And then there's the mid-continent rift all kind of bundled up in there too. Okay, and so we're going to look at the Lake Superior craton first here. And this makes up the majority of the rocks you would see if you're in the Boundary Waters. As you can see on this map. So these are where those Canadian Shield, really old rocks form. And so the different colors here are different, what we call terrains. So again, those little pieces of land that would have been assembling together into larger continents in this time, about 2.8 billion years ago. So we have the Wawa and the Wabigoon are those volcanoes. They would have been little islands. And then the Quetico province there are sediments that would have been in an ocean between those two islands. And they got kind of jammed up together. The Minnesota River Valley is down there. It's not in the Boundary Waters, but if you are from Minnesota, you're probably familiar with the rocks there. That's like the Morton Gneiss is what it's called. And it's that, it's like a beautiful pink and white layered rock that's really, really old. But they use it on a lot of buildings in Minnesota and actually around the country. It's a really good decorative building stone. Cool. And so we were looking at everything from map view before, like we were looking down on it from above. And now we've sliced into the Earth's crust and we're looking at it from the side. So we call this in geology a cross section. And so you have that Wawa subprovince here and the Wabigoon subprovince. So there are these volcanic islands and the Quetico would be underwater in between them. And then these dark slabs that have the arrows pointing down are oceanic seafloor. And what's happening there is they're getting, as the Wawa and the Wabigoon get closer and closer together, that seafloor has to go somewhere and it subducts underneath. And that's the force that's kind of pulling these subprovinces together. So this is sort of like what it would look like over time is that the Wawa and the Wabigoon are far apart and that slab in between them starts subducting and pulls them closer together, the Quetico getting jammed in between. And so what happens when those slabs subduct is they get down into the Earth's crust and they get hot and they start melting. And so that's what's feeding these volcanic islands in the Wawa and the Wabigoon. Awesome. And so another thing that happens because these rocks are really old is what we call metamorphism, where the rocks from this time period, before they got sort of uncovered by the glacial erosion billions of years later, they were buried deep underground. And so the heat and the pressure down there kind of cooks them. It doesn't get so hot that it melts them and turns them into liquid rock, like deep in the earth, but it's hot enough that it changes the minerals and chemicals in them and the structure of the rock. So a way to visualize what's happening is on the left here, we have granite. So you can see there's just kind of a random arrangement of pink and black and white grains kind of scattered throughout. And as they get metamorphosed, it turns into a rock we call gneiss, which is, you can see there's like that layering. So like the black grains and the pink grains and the white grains have been squeezed together into layers as they've been metamorphosed. So that's sort of what's happening in the Wawa and the Wabigoon. So you might see granite and you might see gneiss in the Boundary Waters. But another really interesting rock is in the, sorry, my neighbor's dogs are chasing a squirrel in my backyard. It distracted me for a second. Is happening on that oceanic seafloor that's getting subducted. And so the oceanic seafloor is made up of a different rock type called basalt. And when basalt erupts, it makes these pillow shapes. So I want to try showing a video to show how that happens. So this is in Hawaii. And let me make sure it's mute it there. But this is what happens under the ocean when new seafloor is created. The rocks kind of come up, and as they are exposed to the air or water, they cool and start forming these pillow shapes. So you can see how they sort of balloon out into all these different pillows. Okay, now I just have to figure out how to, okay. So today, what those pillows look like is a rock called the Ely greenstone. So here you can see they have these pillow shapes from that lava that was on that seafloor between the Wawa and the Wabagoon. And if you look closely, you can occasionally see places like I'm pointing to now where maybe you can convince yourself it's a little bit green. But these rocks are, I mean, they're 2.7 billion years old. So they've weathered a lot, and that makes them look kind of dull. But if you crack them open and get a fresh surface, you can really see the colors well. And so here's a piece of greenstone where you can still see those pillows all through there. But you can't, but it's been cut into, and so you can really see the green color come out well. If you were to take a chunk of this in your hand and look at a fresh surface, it would look like this. So this is what that greenstone would look like if you get a chunk of it. And so geologists have spent a long time trying to figure out how these greenstones come to be. It's like actively researched right now. People are trying to figure out like how exactly these form and how they relate to the granites that you'll see in other places. But this is something you'll definitely see in the boundary waters. And a little bit later on, or actually on this next slide, I have some places where you might see that. So this is from a report from the University of Minnesota in the 1970s, had a list of common rocks and where you might see them. So this Ely greenstone you might see on Moose Lake or Knife Lake or Gabi-Michigami Lake. So keep an eye out if you're there for these kind of pillow structures or rocks that are tinted a little bit green. The other one you'll see is this granite. So again, it actually will probably look more like this when you first see it without those pillow shapes, but because of the weathering that's happened, that makes it kind of gray. But if you look up, this is up close, so this is probably about the scale of a quarter or something. You'll see a bunch of little fine-grained crystals in there. And so granite is probably the most common rock that you'll find in the bulk of the boundary waters. And these are some good places where if you want to go looking for granite, but you shouldn't have to look too hard for granite up there. So that is kind of a summary of the Canadian Shield, which I know went by really fast. And as I said, I could probably spend 2 hours talking about the Canadian Shield. But it's this time where all these little pieces of Earth's crust are getting jammed together and forming the continents as we know them today. And that was happening about 2.7 billion years ago. And you see these kind of strips of alternating greenstone, granite, and gneiss in this area in the Superior Craton. And it's so in the boundary waters specifically, what you're seeing are the Wawa and the Wabagoon volcanic belts, and squeezed between them is the Quetico subprovince. Okay, cool. So now we're going to move on to the Pinocchion orogeny, which I'll define what that word means here in a second. But so yeah, we just went through the oldest rocks in the Superior Craton. Now we're going to jump forward 1 billion years to the next major geologic event, where we get these iron formations. So back to this map, just as a reminder, we're now looking in this stippled area between the Mid-Continent Rift and the Superior Province. So most of the Pinocchion orogeny are actually rocks you would see in Wisconsin, but there's a little bit over on the Minnesota side of Lake Superior too. Okay, so orogeny is a term I've been using that's probably not familiar to a lot of you, but basically it just means an event in geologic history where mountains are built, like where something that's flat gets kind of jammed up and turned into mountains. And there's a couple of, it happens in different ways. So it can be an oceanic crust subducting, like I was talking about subduction earlier, under the continental crust. And that gives you these volcanic arcs on land. So this is like the Andes Mountains in South America. This is what's happening there. The other way is if you have two continents that collide into each other. And where that's happening right now is India is colliding into Asia. And that's why you have the Himalayan mountains being really, really tall and the Tibetan plateau up behind them. Okay. But the Pinocchies is a little bit more complicated than either one of these diagrams. So it's a mountain building event, but it's not just one mountain building event, really. It's kind of a series of them. And so the best analogy I've heard of how this works is if we imagine, this is just a picture from Google Earth of today. So you have Australia down in the south, the Australian continent, and in the middle you have Indonesia, which is a string of volcanic islands, and up in the top is mainland Asia. And so what happened in the Pinocchian orogeny is that this the Australia sort of started moving north and collided in with the with a volcanic belt. So of course it wasn't Australia, it was a older subcontinent called, we'll get to that later. This is just the modern analog. And this all collided into mainland Asia. So you have this mini continent colliding into a volcanic belt, which then collides into a bigger continent. So in the Pinocchies, that bigger continent would have been the Superior Craton, the Canadian Shield that we were talking about just a minute ago. And then there was a volcanic arc out in the ocean, and then the mini continent, which was called the Marshfield terrain. And so, yeah, the mini continent moves up into those and then collides all together. And so I'm going to go back to the cross section to show a drawing of what was happening 1.8 billion years ago in Minnesota and Wisconsin. So you have that Superior Craton, and then there's some ocean and what we call the Wisconsin magmatic terrains, which is the equivalent of Indonesia. And as this subduction happens, like I was talking about earlier, where the ocean gets pulled underneath the land masses, it pulled it closer and closer together. And then the Marshfield terrain comes in and they all collide and jam up and make a big mountain range. And I think it was something like 500 miles long and 80 miles wide was the dimensions of this collision zone. So a really big area of what at the time would have been really tall mountains jamming these three things together. And what makes this time period so important is that what was happening in these oceans, and that is the deposition of iron formations. So this is a banded iron formation where the red layers are a iron-rich kind of like relative of quartz, which is a common mineral, and then the middle layers are like a mudstone. So something was happening where all of a sudden a bunch of iron would be deposited in the ocean, and then there'd be a time period where iron wasn't deposited and it recurred in layers. And so I actually have a piece, I don't know if you can see me, but a piece right here with me that I found in a gravel quarry in southern Minnesota back when I was in college. where you can see these banded iron formations. And it's really heavy. It's a really dense rock. And if we look at the map of the Lake Superior region, each of these red areas is an iron range. So the Mesabi Range is one of the more important ones to Minnesota history, but there's a bunch in the UP of Michigan, and in northern Wisconsin is the Gogebic Range. So some people call the Gogebic Range the Pinocchion Mountains because it all formed during this time. So now I want to talk a little bit about why we have this iron formation, because it's an extinct rock type. It doesn't get deposited today. And in fact, this iron formation in the Pinocchies that we have in Minnesota is one of the youngest iron formations in the world. So they're a really old rock type, and they don't exist anymore. And it has to do with oxygen. So I'll get to that now. So this is a picture of a banded iron formation that I think is from the Sudan mine in Minnesota. And so basically what happens to create these iron formations is that in the oceans, you have input from land, you have volcanoes underwater, and you have hydrothermal vents. And all of these things are putting iron into the water. In today's ocean, as soon as the iron goes into the water, it bonds on a chemical level with oxygen and basically rusts out. And so it can never accumulate in the ocean because it disappears from the ocean and as soon as it hits the water. But back in this time, in 1.8 billion years ago, in this little ocean between the marshfield terrain and the Superior Craton, the oxygen levels in the water would have been really, really low. There weren't that many, there were no plants, I don't think. But there were a bunch of bacteria that did photosynthesis, but not on the scale to make the atmosphere as oxygenated as it is today. So I think the estimates I'm familiar with say that the atmosphere had about 8% oxygen, and I think it's like 20% today, if that sounds right. But so oxygen was a lot lower. And what that meant is that as soon as oxygen, or as the iron went into the water, it didn't rust away immediately. It would stay dissolved in the seawater because there wasn't enough oxygen to make it rust. But then if something happens and oxygen levels rise, then that iron rusts out and is deposited on the seafloor. And so what we're seeing in these bands of iron versus not iron is when basically during this, like the time when there's not much iron being deposited, there's not much oxygen in the water. And so the levels of oxygen in the water, or the levels of iron in the water, build up and build up and build up. And then suddenly you have an influx of oxygen from those early photosynthesizers, and then the iron layer is deposited. And so, yeah, as I said, because there's so much oxygen in the world today, this doesn't happen anymore. It can never accumulate enough to deposit one of these iron layers. So when we mine this rock, we're mining something that like can't happen again. And so these iron formations in Minnesota and Wisconsin and Michigan, but also in Australia and South Africa, have been the main source of iron ore throughout all of human history. And so, yeah, Minnesota is home to one of the major ones. And so in the boundary waters specifically, you might be able to see a bit of the iron formation near Gunflint Lake. It's kind of probably the best place to try to see that. Although I think the best chance of seeing it is in the debris left behind by glaciers, which we'll talk about in a little bit. So there's a couple of other rock types from around this time that are important to mention. And the first one is that this slate or mudstone. So that this was also deposited in those oceans around the time of the Pinocchion orogeny. And it's just mud that's been turned into a rock. And so you might see these northeast of the Gunflint Lakes is where this rock type is dominant if you get up that far. And then the other one that's really cool, and I wish I had more time to talk about it because it's a fascinating story, are these what they're called impact breccias. And breccias are bits of broken up rock that have been redeposited. So you can see there's all these like big chunks that are held together of different rock types, all broken up, sharp edges. And this happened because of like the second largest impact of Earth by a meteor happened in Sudbury, Ontario. And the tidal wave of destruction that came out from there was so big that you can find these rocks from this impact, like out on the Gunflint Trail. If you ever go into Thunder Bay, there's some really good outcrops of it too in Thunder Bay, up in Canada. So that brings us through the kind of basics of the Pinocchion orogeny. So it's this time of the North American continent still being amalgamated together. So we're adding on pieces still, we're building it up. And these sequential collisions formed a big mountain range that's called the Pinocchion orogeny. I see a question in there about when the Sudbury impact crater happened. So that happened right at the end of the Pinocchion orogeny. So 1.85 billion years ago. That's 1,850 million years ago. And it sort of marks the end of these iron formations too. I don't know if that's related, like if the impact caused some condition on Earth to switch so that the iron couldn't be deposited anymore, but it lines up pretty neatly, actually. And so in the boundary waters, you might be able to find some iron formation, especially in the little pieces of debris left behind by glaciers. But you might also see these mudstones and impact breccia from the Sudbury impact. And so these rocks are going to be a lot less common than the granites and greenstones from the Canadian Shield in the boundary waters, but they're still an important part of the story, the geologic story. Okay, so we're going back to this to move forward in time. So we looked at the oldest rocks, the Superior Craton. We looked at the Pinocchion orogeny, and now we're going to look at what's called the Mid-Continent Rift, which is when all the copper was deposited. So just to reorient us in space, the Mid-Continent Rift is this gray area that basically kind of forms, it's the ancestral basin of Lake Superior. And geologists actually found out about this when they were looking at what are called gravity anomaly maps. So here, someone flew an airplane above all this land and towed behind a magnetometer, a gravitometer that could measure how strong gravity was with tiny variations across the Earth. And when rocks are heavier and more dense, they actually cause gravity to be larger, to be stronger. So what you see here, this area that they've highlighted in red, is some really high gravity, high density rocks that go from Lake Superior and down through Michigan, but also down into Oklahoma. And so they were puzzled as to what the heck is going on here when they found this gravity anomaly. And so I guess it actually goes right down by the Twin Cities, where it crosses the Minnesota-Wisconsin border there. Here is like Taylor's Falls State Park. You can see these rocks really well, or like up on Palisade Head, you can see them really well on the North Shore. But eventually we were able to figure out why these really high gravity rocks were there. And so I'm going to take you to a cross section. And so basically we start here with the Superior Craton and the Pinocchion rocks all nice together in one gentle layer. But these arrows are showing us that something happened where they started spreading apart. And what we currently think is that all of the Earth's land masses were gathered together in a supercontinent. So it's an earlier one than the one you might have heard about, Pangaea. But when you have all that land gathered together, it traps the Earth's heat down below. And so it got hotter and hotter. And where we are around Lake Superior would have been right in the middle of this big supercontinent. And it got so hot that it started to melt. And when it melted, it started to sort of push apart. And so that's what we see in this next image here. So you can see that fault, that fracture has activated, and it's that this block over here has slid down while the sort of intervening space has filled up with this green is are volcanic rocks. So like basically what you'd see today if you went to Iceland or Hawaii, there were volcanoes all over the Lake Superior region and filling up this basin, making this sort of U shape of volcanic rocks. And as it continued, the rift got bigger and bigger. So basically North America is about to split into two parts with an ocean in between, because these rocks, these green rocks, are the same kind of rocks that you have on the bottom of the ocean. So we're about to have Duluth become a seaside resort, not just a Great Lakes port. But then something happens when it gets jammed shut and jammed back together. And they think that what happened is that what is now South America slammed into the eastern coast of what is now the United States and like jammed that rift shut. And then the yellow rocks that are up at the top of this cross section are sandstones that filled in this basin, because the salt, remember I said they're high gravity, they're really dense and heavy, so they sink into the Earth's crust, and they make this basin so it fills in with sandstone. So if you go to like the Apostle Islands National Lakeshore, or pictured rocks in the Upper Peninsula of Michigan, you'll see these bright red sandstone cliffs. So that's what filled in this rift. I see a question in there that were the mountains eroded by this time? And that's a good question. Those Pinocchion Mountains, probably, because this is happening 700 million years later. And for reference, the Appalachian Mountains were built about 1 billion years ago. And so they've been ground down pretty well over the last 1 billion years. And so these Pinocchios would have been 700 million years old. So I don't know for sure, but I'd guess that they were pretty well ground down by erosion. Okay, so yeah, and then it got that. This is where it starts getting jammed back together, and it makes this broad U shape that basically defines the edges of Lake Superior. So on the right side of that U shape is like the Keweenaw Peninsula, and on the left side is Isle Royale. So some rocks that you're likely to see in the Mid-Continent Rift. The first is gabbro, which is a volcanic rock that forms deep underground. And this is called the Duluth Complex. And it's actually involved in a lot of the copper that we'll talk about here in a few minutes. And this is what it would look like if you were to break off a chunk and have it in your hand. Another rock you would see up there is basalt. So like you're used to in Hawaii or Iceland. And that's where you see these kind of columnar jointing. So it looks like you can see these columns. That's very typical of basalt. So Palisade Head is a great place to see that on the North Shore, or Taylor's Falls State Park, a little closer to the Twin Cities. And then if you hold it in your hand, this is what it would look like up close. And you'll notice there are all these little sort of holes that fill in with something else. And that's really important to the story, that it has these holes that fill in with something else. So in the Lake Superior region, one thing that these holes fill in with are Lake Superior agates. So over the 1 billion years since there was this was active, those holes have filled in with silica, and that turns into agate over time. So you can thank the Mid-Continent Rift if you like to go rock hounding on Lake Superior. And they also filled in with copper, especially over in the Keweenaw in the Upper Peninsula of Michigan. So they filled in with this is just pure native copper. So if we go back to look at this U shape, so here we're going from Isle Royale to the Keweenaw. What was happening is that deep down in the earth, so down at the bottom of this U, there were these fluids like water that was really hot and acidic, and it was pulsing around. And what it did is it took these tiny amounts of copper and silica and concentrated it, and it started moving up the arms of the U towards the surface. And eventually that water cooled off enough and dropped acidity, so it became less acidic, and it couldn't hold the copper anymore. And so it filled in those holes in the basalt up here and in Isle Royale too. So that's where you get that pure native copper. But you also get copper over here in the Thunder Bay region, which, sort of this then extends down kind of along near where the Iron Ranges are. But this copper is different. It's not pure native copper where it's just the element copper on its own. It's bonded to sulfur. And so these kind of dashed lines here, that's the Canadian Shield. And so that copper that's bonded to sulfur is what we see in the Boundary Waters area, and that's pretty important. So for the Mid-Continent Rift, North America almost split in half 1 billion years ago, and there were a bunch of volcanoes, and it created a small ocean basin that then filled up with sandstone. It led to copper deposits, where in some places you have native copper and in other places you have copper sulfide. And it was sort of the predecessor to Lake Superior. Okay, so we've gone through the oldest rocks, the Pinocchion orogeny, the Mid-Continent Rift, and now we're on to glaciation. And I'm running short on time, so I'm going to go a little faster through this. But basically, glaciation happens because of climate. If it's cold enough, ice sheets grow. And so on this chart, we're seeing along the x-axis time. So the youngest time is here, and it gets older as you go to the right. And on the y-axis is a measurement of ocean sediments that tells you how hot or cold it was. So what you need to know is that at the top of the chart, when the line goes to the top of the chart, it's hot. Like today is pretty warm. There's no glaciers on North America. And when it goes down to the bottom, it's cold, and North America gets covered in ice. So this gives us a sense of the scale. So today there's just ice on Greenland, but like 30,000 years ago, the ice sheet would have covered all of northern North America. So here's Wisconsin and Minnesota and Lake Superior, right in this region. And just to give you a sense of the scale, this is someone in Greenland now, and there's little people, but they're not even, you can't even see the bottom of the ice sheet here. They're like miles thick. They're massive, massive, and so they can make huge changes on the surface of the earth because of their weight. So one of the things they do is leave behind what we call till, or a lot of older farmers call it boulder clay, because it's boulders jumbled up with clay, which the only time that really happens is underneath a glacier. So when you see rocks like this, it was from a glacier. It's the debris left behind. But if we look up in the Boundary Waters, up in the Arrowhead region, what the depth to bedrock means is that there's not very much of this in the Boundary Waters. So there's at most 50 feet, but I think in most of the Boundary Waters, any glacial deposit is probably like 15 feet thick. Compared to if we go over here into more north central Minnesota, we're looking at like 500 to 600 feet thick of glacial deposits. So what that means is that up here in the Arrowhead, the glaciers scraped away, but they didn't deposit as much. So a lot of the stuff that got scraped away up here was deposited in these thick areas. But even though they didn't deposit anything, they still shaped the landscape. So here we're looking at like the US-Canadian border through the north unit of the Boundary Waters. Gunflint Lake is there. And these lakes are facing east-west. And so for a while, people thought that meant the glaciers flowed from east to west. But they found these striations or scratches on the rocks made by the glaciers that showed that it actually flowed north to south. So why do we have these lakes that face east to west? And it turns out that it's because the glaciers scraped away all the loose rock and soil and debris that was on top of the solid bedrock. And so what we're seeing here are actually the remnants of like that mid-continent rift time. So everywhere there's land is a stronger layer, and everywhere there's a lake is a weaker layer that was more easy to be eroded. And so this would be like maybe one of those iron formations or a basalt, and then the weaker area that was eroded would be a mudstone or something like that. And this is one of the few places in the world where you can see the bedrock so clearly. And we have the glaciers to thank for that. So even though there's not a lot of glacial geology up here, we have the glaciers to thank for the fact that we can see all these really, really old rocks up there. Oh, and then this is just a map of the geology again, a geologic map that shows that those structures run east to west. And so we're seeing the geologic structures in those lakes rather than the glacial scratches, basically. The other thing that glaciers leave behind are called glacial erratics. So there are these giant boulders that get left behind by the glacier. So that's something you will see a lot of up in the Boundary Waters are these glacial erratics, big boulders that are just kind of out of place. They don't match sometimes the rocks around them that are not out of place, that are in place. And I don't want to spend too much time on this because I'm running out, but basically what this map is showing, this is from a draft publication that the Minnesota Geological Survey was kind enough to share with me, but the white part is ice. And so this was a point in time where we're covered in ice, but this blue area is a glacial lake. So the glaciers build these dams and it causes water to build up. And so there's at one point a glacial lake that covered most of the Boundary Waters. So this started at about 2.5 million years ago. The ice sheets grow and retreat. They go back and forth. And in the Boundary Waters area, they removed soil and other decomposed, kind of broken up rock, exposing the Canadian Shield and the Mid-Continent Rift and the Pinocchion orogeny. They left behind that glacial till or drift and erratics, and really were responsible for shaping the landscape. And so I also want to make the point that we've gone through all of these geologic events, but geology doesn't stop in the past. It continues today. So we're in the present and things are happening now geologically. And one of the main ways that geologic things happen on our time scale is through the movement of water. And this is where that mining comes in. So this is for the Twin Metals mine, but it's a similar geology to the Polymet, which is the one near the Boundary Waters. And so this is the Mid-Continent Rift, is this gray rocks. This is the Canadian Shield in the pinkish, and in between them is that copper sulfide mineralization. And because it's not pure copper, the waste of it is really rich in sulfur. And so that's what we're worried about, is that if this sulfur waste gets into the groundwater and moves through the water, so that there's the copper sulfide again, it can contaminate our pristine waters of the Boundary Waters. And I'll just go through this quickly, but it used to be that we thought that water just moved through spaces between grains in rocks, but in groundwater, but in the Boundary Waters, it's this crystalline rock. So this is granite and there's no space between these grains. So some people assumed that the water wouldn't flow through. But here's a geologic map again. And what we can see is that all these black lines are those faults and fractures. So you've seen this talk, you know how much these rocks have been through over the last 3 billion years. And so there's a lot of fractures and cracks. And so that's how the water can flow. So that brings us to the end. Thank you. Sorry I had to rush there a bit at the end. But if you want to learn more, I recommend these books: The Roadside Geology of Minnesota, The Geology of the Lake Superior region, or you can check out my podcast. I talked about the Pinocchion orogeny, the Mid-Continent Rift. Friends of the Boundary Waters Communications Director Pete Marshall appeared on episode 5 about wild rice and copper sulfide mining. Also, Frank Bebo, who's a White Earth Ojibwe lawyer who's suing for the rights of Minoman, and then an episode about glaciation. So yeah, thank you all for listening. I'm really glad that I got to chat with y'all today, and I'm happy to answer a few questions.
Great. Well, thanks, Rudy. Yeah, that was a great presentation, really interesting information. And just for folks that are wondering, I will send out some of these links in a follow-up email, as well as a recording of this presentation if you want to watch it again or want to pass it along to somebody else. We've got time for a few questions here. We probably won't get to all of these, but I will ask as many as I can. I see the first one that pops up is someone wondering, has the Laurentian Shield or Continental Divide moved over time?
So I guess if I'm interpreting this correctly, the stable core of North America, has it moved around the globe over time? And it definitely has. So that's these continents, they spread apart. We have supercontinents that jam together, but then there's these rifts. So the continents are constantly moving, and they're moving still today, and we can actually track it with GPS. So North America right now is moving apart from Europe at about the rate that your fingernails grow. So every time you clip your fingernails, you can just think you're that much farther away from Paris.
That's a great fact. Somebody was wondering, at the beginning of the Precambrian age, was there any land mass that was above water?
I don't know the answer to that off the top of my head. I think that that's something that people debate. They try to find out these trace chemicals, tiny amounts in the rocks that might indicate whether or not it was above water or below water. But I'm not sure off the top of my head. I think there were some, and that's where some of these kind of first bacteria evolved.
Great, yeah, that makes sense. Let's see, we can do one more question. Somebody is wondering, how were the mountains that you mentioned ground down with no glaciation? So was it rain or was it some other process?
Yeah, so I mean, 1.8 billion years is a really long time. So rain does a lot of the work of erosion, so does rivers. There may have been ice sheets way longer ago in the past. Like they think there were times 1 billion years ago or something where the whole earth was covered in ice and snow. So not just part, but all of the earth. We call it snowball earth. So there's lots of forces that act on erosion, and the land surface that even today that you walk on is a balance between things trying to rise up and things trying to tear it down. And it's just constantly an ongoing process.
Great, yeah. Well, it's super interesting. So many more questions that unfortunately we won't be able to get to today, but Rudy, if you're able, I can share your email if people have follow-ups, or I can kind of facilitate the questions as well. And I just want to echo, a lot of people in the comments or in the chat have really commented how much they enjoyed this presentation, found it very informative and engaging. And so we're all very grateful to have you on, and grateful to have you, helping us understand kind of all of this history. It's been a great learning experience for me. So yeah, we've hit 1 o'clock. I'm going to wrap it up here. Just want to say thanks again to all of you for joining, for your support of the Boundary Waters, and thanks again, Rudy, for your presentation. Look out for a follow-up email from me probably today or tomorrow that will have the link to the recording and some of this extra information as well.
Thanks so much, everyone. And yeah, feel free to email me. It's up there on the screen right now, and it sounds like Maya will send it out as well. I'm happy to answer any follow-up questions later.
Great. Well, thanks again. Have a great afternoon, everybody. Bye-bye.